So now we'll talk about parametricity and the LP, and Vojtěch will give the talk.
Thank you for the introduction. I'm happy to be here and be presenting this joint work with Cyril Cohen on implementing parametricity in Rocq-ELPI. And what exactly do I mean by implementing parametricity? Well, on paper, parametricity is a property of the type system we're interested in, and it's linked to this relational interpretations of this type theory. And in this talk, I want to assume this point of view where it's not just a theoretical tool for proving things about our type theory, but really a practical tool for code generation, generating theorems and definitions. And how can we do that? Well, in dependent type theory, we have this advantage where relations are kind of a first-class thing because they are really just functions into a universe. So we can implement it as a translation from terms to terms in the same theory. And I prepared a couple examples for what kind of things this code gen tool can do. There is this library for doing data type refinement in Coq called Rocq-EL, which the idea is usually you have this proof-oriented and a computation-oriented data structure, and you're trying to push all of the various computations to the computational part, and then you get a nice theorem that you compute it very similarly to how you would compute in the proof theoretical or a proof-oriented structure. This generalizes to this notion of proof transfer, implemented, for example, in the library Rocq, where you don't only transfer computation, but you can also transfer properties. This is a very nice example of what Rocq can do, where you have this statement about universally quantified over natural numbers, and you can show that it holds by reducing to a computation in Z mod 9, where you can check just a finite number of cases. And the last example I want to show is generating these displayed objects, which is currently implemented in Rocq-ELPI, which allows you to derive dependent versions of your various data types and then use those in your generated inductive principles. And I'm sure that over the past week you've heard many presentations which in the concluding remarks say like, well, and this is probably some sort of parametricity, we're not really sure what the link is. Well then, once they figure out what the link is, they can use this thing. And the way this is usually presented is that we have this translation of contexts, where this is specifically the case of binary parametricity, where a variable in the environment gets translated to 3 variables in the environment, one which shows that the previous ones are related, and then you go on and you translate your terms, and that's all good and nice, but there's this notion of priming of various terms, and it's not entirely clear what this operation does. And now I see that probably the blue background isn't very well visible on the display, so that's not great. It works? Okay, so it's just my angle. Never mind. But it doesn't really help clear up what this priming operation does, right? The essence is that we are running 2 translations. One is for duplicating variables in the context, and the other is the actual essence of parametricity that we want to get into. And when we are implementing parametricity, we need to care about freshness of variables, which is annoying. We can solve this either by going De Bruyne, or we can handle state manually and pass it around, but we don't really want to, because that's just not great, and it's not obvious that this is something that we should care about from just reading the paper translation. And if we zoom out, we realize that this problem really asks us to handle 2 things. One is induction on syntax, and the other is nice handling of binders. And in the mainstream metaprogramming frameworks for Rocq, such as Ocon plugins and MetaRocq, we can do induction, because what language now can't do induction, right? But the binders are still pretty manual, and De Bruyne indices are susceptible to subtle errors and whatever. And so it's not great, dare I say, it's a little rocky. And that's why we turn to Rocq-ELPI, which stands for Rocq, and Embeddable Lambda Prolog Interpreter. And it's a layer on this LP thing, this Lambda Prolog with Rocq bindings. And the nice thing it does is that it gives us higher order abstract syntax representation for Rocq terms and top-level declarations. So again, I have these two examples, which this part isn't really important. The important part is that the body of the function is represented by a function in LP, which you'll notice that the variables are written on the left of the backslash, but that's something you just get used to. And this holds for both terms, and I also have this inductive data type, where once again, the list of constructors is constructed in a context where it has a variable, an LP variable for the inductive and an LP variable for the parameter. And if you're still not convinced, then, well, like, look at the name, right? It has exactly the two things we need to do. We need to do binders, so we have lambda, and we need to do induction, so we have prolog. So hopefully we're now all convinced that this is the right thing to do. And since now we know that we will be implementing things in a logical language, we will switch from this functional style description to a sequence style description, which you can read more about in the series of papers on Rocq. And essentially, we have this judgment that in a parametricity context psi, t is related to t prime because of tr. And t prime and tr are outputs in this judgment. So we have a variable for, we have a rule for the variables, we have a rule for the types, just as before. And I want to particularly focus on this rule for lambdas, where we have like the semantics are the same, right? A lambda is related to a lambda because of the translation, which we've already seen. But the way that we conclude this is by first looking for the translation of the type, and then assuming that we have these fresh variables which are related, and we derive that the bodies are related. And this can be very elegantly implemented in LP by this param-Turner predicate. And the way we do it is that each rule, each inference rule, gets a clause. And we start by writing out the conclusion of the judgment in the clause head and proceed by running the body, which we first implement some sort of naming for pretty printing. That's not really relevant. Then we query the context for the translation of the type, and then we universally quantify over 3 fresh variables, assume that they are related, and then ask LP to give us the outputs t prime and tr with the right variables in scope. If I had more time, this is where I would pause so that you can all go ah, but I don't. And then there's this administrative thing where we need to convert between a lambda function as a Rocq term and a lambda function as a LP function, but like that's variable. And the last part that I prepared is that this translation is usually given for terms in CIC or CC omega, but we need to scale this to be able to like use it as a practical tool in Rocq. And this brings a couple complications. I will talk about 2 of those. One is that Rocq's unfolding of fix is conservative. So some of the definitional equalities that the paper translations usually assume do not hold in Rocq, because the scrutiny of the fix needs to be constructor-headed. So we fix that by just inserting some trivial matches so that the argument is constructor-headed. And the other part is handling records, which in the literature, usually those are represented by an inductive with 1 constructor. But that doesn't really work if we want the translation to be a record again, because if we start with this record, translate it to an inductive, what we get by the parametricity translation is an indexed inductive. But we don't have indexed records. Like, what does that even mean? We really want the translation to be a record which has these 2 instances of the original record as parameters, and then uses projections in the fields instead of building up an instance of the record in the index of the output. So it's pretty straightforward to adapt to this, but it's something that one needs to be aware of. And the other thing is that the records and inductives are not necessarily exactly dual, because for inductives, we have this universal eliminator in the core syntax. That's the match statement. And we know how to translate a match statement pretty continuously. But records do not have this analog of like a universal constructor. So what we need to do is show you some scary types. We observed that relating projections by projections is okay. And you just need to trust me that this justifies that this relation is okay, because all of these things have the right types. But if we try to do the same thing for the constructor, that's not okay, because here we're assuming that the constructor should have all of the arguments of the fields unwrapped, while actually the real constructor that we are trying to use here has the arguments bundled as instances of the original record. And inductives get, so we need to generate some shims that we need to insert here instead of the actual constructor. We need to just wrap the constructor and rearrange the arguments a little bit. The same thing would need to be done for inductives if the primitives were the inductive eliminators. Which brings me to the end, where I will say that most of what I talked about is already implemented in the standard distribution of Rocq-ELPI, so you can use it now, except for the records. We haven't upstreamed those yet, but those are coming whenever I get to it. And this implementation is already used in Coq-EL, and Rocq is a bit more complicated, so they hand-roll their own implementation, but it uses all of those same ideas. I think it's fair to say that there is for now a caveat where Rocq-ELPI does not allow for representing mutual inductive types. Sometimes that bites you a little, but like you can get away with some workarounds. And I would encourage all of you to give Rocq-ELPI a shot. It makes programming fun again. Thank you.
So earlier you said that we do not have indexed records. Unfortunately, Rocq's kernel accepts indexed records, but we still do not know what they mean.
Yeah. Yeah, I was wondering whether I should mention this, but.
So actually it's funnier than that. It's like the elaboration is preventing you from writing it, but if you directly metaprogram them, then you can make them accepted. Because the check was done at elaboration and not in the kernel. And
so where's the limit for the mutual inductive types? Is it because you can't program them, or is it because the user interface to receive the mutual inductive types is not there?
The higher order abstract syntax doesn't have a representation for them.
It's a minor point, but at some times there were a problem with the guard condition, also with the parametricity translation. Because subterms sometimes get expanded, so like a constructor, when it becomes dependent, instead of being a variable, becomes a successor of something. Mm-hmm. And this breaks the guard condition, so this happens for some example, for instance, in the standard library. So do you have some, does it work, what you did for that, like for this example? So I believe, 1 year ago, there were a problem still.
I'm not sure. I didn't focus on this thing explicitly. I'm aware that there was an issue on GitHub for something to that extent, but as far as I know, this was kind of like before I started working on this implementation, so better ask Cyril.
The example is you take GCD typically. You try to do parametricity for GCD. Does it work or not?
I haven't tried. But it's a good test case. Thank you.
And next, thanks, Stefan, for
Thank you
again.